Hello everyone, my name is Yujia Liu from Peking University. I would like to give a brief introduction to our accepted paper, Enhancing Adversarial Robustness in SNNs with Sparse Gradient. This work is a collaboration primarily with Fu Tong and Zhao Feiyu. For more detailed information, please refer to our full paper and code using the QR codes provided. My introduction contains 5 parts. Now let's move to the first part, motivation. In this paper, we focus on classification tasks using stacking neural networks, shorted for SNN. We find that SNNs exhibit good robustness against random perturbations but display poor robustness to adversarial perturbations. For example, when we randomly sample perturbations within an L-infinity bounded ball with a scale of 0.1, SNNs still achieve over 80% classification accuracy on CIFAR10. However, when attacked by FGSM with a perturbation scale smaller than 0.05, the classification accuracy drops to nearly zero. Therefore, the main idea of this paper is to quantify the robustness gap between random attacks and adversarial attacks, and then reduce it to improve the robustness of SNNs. To quantify the robustness gap, let's first introduce some notations. Given an SNNF, an input image X is the true label Y, and Fy is the output of F, which determines the classification result of X. We define the vulnerability of the SNN and the random attacks as the expectation of the change in Fy. A larger row rand indicates a greater expected change in Fy and the random perturbations, implying poor random robustness. On the other hand, adversarial perturbations lead to the maximum change in Fy. So we define rho ADV as the superior of the change in Fy. A larger rho ADV indicates poorer adversarial robustness. According to these definitions, we can quantify the robustness gap by the ratio of rho ADV and rho rand, and we prove that this ratio is upper bounded by the L0 norm of the gradient, which also represents the sparsity of the gradient. Based on the theoretical analysis, we propose the sparsity regularization training strategy to improve the robustness of SNNs, which is shorted for SR strategy. Specifically, let's consider an SNNF with a final layer denoted as capital L, and SLI is the bandwidth spec of the nth neuron at time t. Then the output vector of the final layer is as follows, where each component is the number of firing specs over the entire capital T time step. Suppose Y tilde is the index of the maximum component in FL, except the width component. We define Fy as follows, since the classification result is not only influenced by the value of Fly, but also by the magnitude of Fly in comparison to the other components in FL. Finally, we incorporate the sparsity of the gradient of Fy into the loss function and use the finite difference method to avoid NP-hard problem and double backpropagation. We conduct extensive experiments on CIFAR10, DVS CIFAR10, and CIFAR100 datasets. However, due to time constraints, please refer to the main paper for the full experimental results. Here, we only present 2 primary findings. The first experiment demonstrates the robustness improvement due to the SR strategy, measured by classification accuracy under different attacks. We tested the robustness of white ResNet 16 architecture under both white box attacks and black box attacks. And we compare our method with SOTA RAT strategy and adversarial training strategy. As shown in this table, SR-trained models exhibit better adversarial robustness in all scenarios. The second experiment illustrates the effectiveness of the SR strategy in reducing the gradient sparsity of SNNs. We visualize the heat map of the gradient for both vanilla SNN and SR-trained SNNs. It can be seen that the gradient of SR SNNs are more sparse than those of vanilla SNNs, where the contour of the object is more obvious. To conclude, in theory, we proved that the robustness gap of SNNs between random attack and adversarial attack is upper bounded by the sparsity of gradients. And in practice, we proposed the SR training strategy and significantly improved the robustness of SNNs. For future work, we will try to find better trade-offs between classification accuracy and adversarial robustness of SNNs, and we will do further exploration inspired by biological vision. Thanks for listening and welcome to follow our work. Thank you again.